So for number 2, it's a chi-square test. So basically that's a test for independence. And here we want to study the question whether ages and the breathlessness is independent or not. So that's the aim of this question. The way we do this is first we assume those two statistics are independent, and we're going to use our assumption to basically construct a table of our expectation. So the table of expectation is built based on our assumption that breathlessness and ages are independent. And then we're going to compare our table of expectation and our actual observation, and to see if they differ by a lot. And if they do, we would say the assumption doesn't hold, and the two are indeed dependent on each other. So first, we're gonna assume independent, right? And a very important, or like the basic formula of independence, is the probability of A and B equals the probability of A times probability of B, if A and B are independent. So we're gonna use this, right? If we assume independence, then we have the probability of aged 29 or less. That's the first probability we have, or namely probability A. It's computed by 3,743 divided by 18,282. So basically you have your total, so you look at your total column and you use the first number divided by the last number. That gives you the probability that a person is less than 29 years old, right? And then we're gonna look at the breathlessness, and basically by the same token, we look at the last row, right? And we use 2,221 divided by 18,282. That gives us the probability of breathlessness, right? So in total there's 2,221 person has the illness like breathlessness, and then you divide it by the total number of people. So we have, like, first we have the probability of aged under 29, then we have another probability, the probability of breathlessness. And if age and breathlessness is independent, then the probability of both of them, right, aged under 29 and have breathlessness, that's a probability of A and B, should equal to the probability of A times the probability of B. So under our assumption, right, your expected probability of both breathlessness and under 29 years old is 3,743 divided by 18,282 times 2,221 divided by 18,282. And then that's a probability, right? And your expected number of people is that probability times the total number of people, which is 18,282. So if you simplify that expression a little bit, because you have the total number of people both in the denominator and in the numerator. So if you simplify that expression a little bit, you get your expected number of yes and less than 29 years old should be 3,743 times 2,221 divided by 18,282. So basically, you want to calculate the expected number of the first entry of this matrix. By the way, your actual observation of the first entry is 48, right? But your expected number of people should be the last column of the first row, like first row intersection last column, that number times the intersection of first row first column and divided by the number in the last row last column. So that's basically the pattern. And so if you do another example, right, less than 29, and now if you want to calculate the second entry of this matrix, you're going to use 3,743 times 16,061 divided by 18,282. So that's basically the pattern, and which shows the expected number of people in each entry, providing that age and breathlessness are independent of each other. And for this question, basically your expected table should look very different from the actual observation, and basically that means your assumption doesn't hold. But a rigorous proof, like the rigorous computation of how different your actual table is from your expected table, is a chi-square statistics. And the way to compute this is you find the like entry by entry, the actual table and your expected table, and you use your observation minus your expectation, and you have the whole thing squared and then divided by your expectation, right? So I'll tell you, like for the first entry, your observation is 48, right? Both under 29 years old and have breathlessness. The observation is 48, but using the formula I just proved, you're gonna find your expectation, which is around 454.7, right? So for the first entry, you have that component in your chi-square, which is you're gonna use 48 minus 454.7, and your whole thing squared divided by 454.7. And that's the first component of your chi-square statistics. And you're gonna do this 6 times. Yeah, you're gonna do this 6 times because you have 6 entries in this matrix. You have less than 29 and have breathlessness. You have less than 29, do not have breathlessness. That's the 2 entry in your first row, and also you have 2 entries in your second row. You have 2 entries in your third row. So basically, you're gonna add those 6 components of the chi-square statistics together, and that's your total chi-square. And you're gonna compare that chi-square with the critical chi-square. The way you find critical chi-square is you have a table, and you should locate a degree of freedom. The degree of freedom is computed by row minus 1 times column minus 1. Here in this matrix, you have 3 rows and 2 columns. So your degrees of freedom should be 2 minus 1 times 3 minus 1, which is 1 times 2. And the degrees of freedom should be 2. So you look at your chi-square table, you find your degrees of freedom equal to 2, and you have your critical value. And then just like your z-score test, like your t-test, right? You compare your computed chi-square with the chi-square critical value, and if your chi-square, if your calculated chi-square is higher than the critical value, then you reject the null hypothesis, which is you reject the 2 things are independent, and that means the 2 things are dependent of each other. And for part B, basically it asks you, right, like how much more likely for a person aged 55 is compared with a person aged 29 or less, right? You want to find the ratio of the relative likelihood of catching the illness. So basically, the first step, you're gonna find the absolute risk, right? So for people under 29 years old, the absolute risk of catching the illness is 48 divided by 3,743. That's your absolute risk. And you could do a similar thing for 30 to 49 years old, and then for 50 plus years old, you have three absolute risks. And then you take the ratio. You're gonna find the relative risk, and intuitively, it's like many times more risky for 50 plus years old than 29 years old or less. So that's your part B. But I think the most important is the part A, like the chi-square test. That gives you like basically it's similar to a previous homework where you're gonna determine if two things are independent or not. Here you use the same thing. Namely, you're gonna assume two things are independent, and you use the formula probability of A and B equals probability of A times probability of B. But then you have one more step, which is you're gonna calculate your chi-square statistics. You do the comparison, right? For your previous homework, a lot of times you just say like the actual observation is similar to the expected observation, or you're gonna say the actual observation is largely different from what we expect. But that's more of a qualitative way to determine if the null hypothesis holds. Here, using chi-square statistics, you have a quantitative way to determine if the actual observation is different from your expectation. That's the only difference.
All right, perfect. I think I got everything. It was really helpful. Thank you.
Sure. I also talk about question one, but if you don't, and then I post the recording. But if you don't have any question on question one, you can just leave.
Okay. Okay, perfect. Just part B. So the risk is just the gross probability of like happening within that age group. Is that it?
Yeah. Yeah.
Okay. And comparing them. Okay.
Okay.
Thank you very much.
So for question A, that's a pretty standardized two-sample t-test question. But here you're gonna notice, right? First you have, because you have Devon and Cornwall, you have like two set of observations, and you're gonna determine if those two have the same mean, right? One thing you're gonna be aware of is the observation. The number of observation in two samples are different. For Devon, you have 12 observations, and for Cornwall, you have 11 observations. So that's the most complicated case in two-sample t-test, where you have different numbers of observation. The way to do this is pretty standardized. First, you find the mean and the standard deviation in Devon, and then you find the mean and standard deviation in Cornwall, and then you calculate the what we call a pooled standard deviation. I think the notation is something like S square P, sort of like it's a pooled pooled variance. Um, the way to do this is you use like N1, the number of observation in Devon, N1 minus 1 times the variance of Devon plus N2 minus 1 times the variance of N2, the variance of Cornwall, then divided by N1 plus N2 minus 2. Notice the the denominator is also your degrees of freedom, n1 minus n2 minus 2. In this case, it's 12 plus 11 minus 2. That's your degrees of freedom. And you have your pooled variance. And then similar to the t-test, right? Similar to the one sample t-test, here you have two sample t-test, right? And in the t formula, your numerator is x1 bar minus x2 bar, right? The mean, the difference of the mean. And in your denominator, you have the pooled standard deviation. And the pooled standard deviation is the pooled variance, which you just calculated. The pooled variance is square p times n1 times 1 over n1 plus 1 over n2. Right, that's just some adjustment because you have different number of observations because here n1 and n2 are different. So in the denominator, that's pooled variance times 1 over n1 plus 1 over n2, and then you take the square root of the whole thing because you have the pooled variance times something. You have your adjusted pooled variance, and then you're going to take the square root and to get your standard error. So that's your t formula. And as I said, after you have your calculated t statistics, you're gonna find your t critical value. The way is first to determine alpha, which here it doesn't say explicitly, but you could like assume alpha is 5%. Then you have your degrees of freedom, and 1 plus n2 minus 2 equals 21 here. So you go to your table, you have your degrees of freedom, you have your alpha, you can locate your t critical value, and then you compare your calculated t with the t critical value. So that's how you answer question A. For question B, you have Wilcoxon rank test. So here the basic idea is you're gonna find the rank, right? You're gonna rank those 12 plus 11, which is you have 23 observations in total. You're gonna rank them, right? So their rank should be 1, 2, 3, 4, all the way to 23, from the lowest score to the highest score. And here the lowest should be 97, which is in Cornwall. And the highest is 182, I think, 182. Yeah, that's in Devon. So basically you just rank them from the lowest to the highest, and you mark them with 1, 2, 3, 4 with their rank, like 1, 2, 3, 4 all the way to 23. And then you're gonna calculate your expected rank of Devon or Cornwall. That's the same, because basically if you have one, then you use the total minus that one. You get the different. You get the other one, right? So here let's do Devon, right? You're gonna find the expected rank of Devon of all the observations in Devon and the variance. The expected value is more intuitively understandable, right? Because you have 23 ranks. So if you assume like those two groups have no different, then the expected rank of each and every observation should be the median of 23, right? 1, 2, 3, 4, and 23. The median is 12, right? So expected rank of each and every observation should be 12. And since Devon have 12 observations in total, so the expected rank of all the observations in Devon should be 12 times 12 is 144. By the way, you have a formula in your class slides, and it says the expected rank of A, let's say A is Devon, should be NA the number of observation in A, which is 12, times parentheses NA plus NB plus 1, end parentheses. So that's 12 times 12 plus 11 plus 1. The last three term has a parenthesis on them, and then divided by 2. So you can locate your formula. And for the variance, it's not that intuitively understandable. But again, you have the formula of the variance of the rank, and the formula is NA times NB times the parenthesis NA plus NB plus 1, then divided by 12. And in this case, it should be 12 times 11 times parenthesis 12 plus 11 plus 1 end parenthesis divided by 12. And that's your variance. And you have variance of your rank, then you take the square root, you're gonna get the standard deviation. So here we can utilize the confidence interval to do it, assuming normality, right? So then we're gonna calculate the actual rank of A, right? You just sum all the marks you gave for Devon, and then you say if the actual rank locates within 95% confidence interval. So the way to find the upper bound and the lower bound of 95% confidence interval is you use your expected total rank of Devon plus or minus 1.96 times the standard deviation of the total ranks. So you just calculated the expected total rank of Devon and the variance of total rank of Devon, right? So I said you take the square root, you get a standard deviation, and you're gonna use the z-score of 1.96, assuming alpha equals 0.5 two-tailed, so it's 0.025 one-tailed. So you have your z-score, and the way to find 95% confidence interval is always your expected value plus some number times the standard deviation. And here you use that number 1.96. It's more of a norm, right? Because you use like 5% alpha two-tailed. And then you're gonna determine if your actual rank lies within that interval, 95% interval. And if not, you just reject the null hypothesis that those two are the same, and concludes like the length in Devon and in Cornwall are different.